Hi everyone. So in this figure you see we have a bar, and once again we're doing a similar problem. We're trying to find how normal and shear stresses would affect how we design this bar. Now one issue is, instead of having an angle, you see that we have right here, we have our nice little slope triangle. Just going to make things a little bit different. Also, it tells us what the width of the bar is, which is 2.5, but it doesn't tell us what the thickness is. We don't have the cross-sectional area to start. And so knowing what the tension load is, and knowing that the stresses on plane AB, this one right here, can exceed 16 KSI and 8 KSI, respectively, we have to determine what that thickness is going to be. I'm going to give just a little bit of help here. Remember that area is going to be equal to the width times T. And that should allow you to plug things into most of your equations and solve for T. Also, whichever one of these will need a bigger thickness is the one you're going to have to go with. You do not go with the smallest thickness. The smallest thickness will fail. The bigger thickness will succeed in both situations. So with that in mind, I'm going to let you go. Try this out. Remember, it's group problem solving, so grab a friend and come back after you've done it to see if you've done it correctly. So 3, 2, 1. Okay, you're back, so let's try this out together. Now we can go ahead and write our general equations for the normal and shear stress once again, but we don't know what the area is. So we're going to have to input that to help us out. We also don't know what that angle theta was, but we can figure that out pretty quickly by using tan of theta. So opposite over adjacent, 3 over 1. So theta is going to be equal to 71.56 degrees. 71.56 degrees. Now, we know that the normal stress on plane AB is limited to 16 KSI. And so we're going to have to try to find what is the minimum area that can support 85 kips, given that. So we're going to take our equation right here, and we're going to solve for the area, which is actually really simple to do, because we can just more or less switch those two. And we do that. And our no area has to be greater than whatever this value is. So we plug in our force. We plug in our stress right here. We plug in our angle. And what we get is 0.5312 inches squared. Okay, 0.5312 inches squared. And you're like, well, what about that AN? Do we ever actually have to calculate the area of this just by itself? Very rarely. That's why we took our time in making these nice equations here. So we don't have to do a bunch of extra calculations. Okay, but now let's do it for the shear stress. Once again, all we're doing is we're solving for the area instead of the stress or the load or something else. And we're going to see how much area this one requires. So we plug it in, and what you see immediately is that this is significantly larger. We were only in 0.5 before, and so this would be the one that is the limiting factor. To hold that shear stress, and this is a pretty common theme here, that usually shear stress is what fails before normal stress. But to hold that shear stress, we would need an area of 3.1875 inches squared. And then from that, we can start to calculate the bar thickness. So we know that area is going to be equal to width times thickness. We're going to solve for T, so it's going to be area divided by the width, which is what we have right here. And what it comes out to be is 1.275 inches thick. They got rid of the 0 simply because this is 4 sig figs. If you have a 1 to start, that's typically what you do. Okay, so we did it. What you saw here is we're going to come back to these equations all the time when we're doing inclined planes. So use them to your advantage. The biggest issue you're probably going to run into is this angle right here. Remember, that is the angle between normal vectors, okay? Angle between normal vectors. If you forget that, you're going to have a bad time. Otherwise, things go pretty fantastically. So, I hope this helps you, and I'll see you all next time. Have an absolutely wonderful day. Bye-bye.